Okay, we have a special Mardi Gras edition of numerical linear algebra. Well, with not many people here, there's plenty to go around. Okay. So, this is what you're missing. King cake, you all.
Is it good?
They're gonna enjoy
Yes.
those sound
But
effects.
I'm also having up yummy noises for the viewing audience.
Oh, food.
Everybody's excited.
What flavor is this? They made these? Or they just sold them?
No, they make them.
They made them, yeah. Can I eat like an obnoxiously big piece?
Well, there's but I mean, I probably would have cheated had I not been. Is it good?
Okay. Well, now the at-home audience is hearing this all eat. But okay. Okay. How's the first homework coming? Okay. Well, I know some people are further along than others. Okay. I received 2, I think, in a class of.
I have one.
Oh,
But
okay.
it's been typed up yet.
Okay. Oh, like LaTeX type up?
Mm-hmm.
Cool. Okay. All right. Now, the first thing I'm going to cover today is going to be very important for one of the problems in homework 2, because this problem is always a pain every year, and yet I statistically give it anyway. But you've been warned that. So. What?
What problem number is this?
Number 3.
No, we're doing all homework.
Yeah, homework 2, number 3. All right. And, well, yeah, I guess it's really as hard as it looks. But, now you know. I've never known an algorithm to have as many names as this one does, iterative refinement. When I first learned it, it was called iterative improvement. It's also called residual correction, and probably other names besides that. This goes to one of the common misconceptions when it comes to solving AX equals B that we're still dealing with for the remainder of this chapter and on into the next chapter. That let's suppose you use some method, such as the one we've been covering, Gaussian elimination and forward-back substitution, to solve AX equals B. And you get a solution, which of course is not the exact solution because there's some error, like round-off error. And let's suppose that is the proximate solution. I should say an approximate solution computed by whatever means. And I'm going to use plain old x, how I always write it, as the exact solution. So x tilde is our approximation to x. Now, we'd love to know what the error is, but of course we can't. I mean, if we could get the true error, then we could just add that and get the exact solution. But here's what we can get. The residual R is defined to be just, you're trying to solve AX equals B. So R is just the difference between B and A times your solution. So something that you expect to be small. You really want it to be 0. Now, so we can go ahead, so once we computed x tilde, of course we can go ahead and get the residual quite easily. So the myth I want to dispel right away is that if the residual is small, that there's necessarily a small error, and vice versa. I mean, it's often true, but you want to avoid falling into the trap of assuming that just because you have a small residual, that it really is an accurate solution. It just depends on the matrix. But there is a simple relationship between the error and the residual. So I'm going to define, so R is the residual. I can define the error to be E, and that's just going to be the exact minus the approximation.
So here you mean relative error? Or absolute error?
This is absolute error. Yeah, because I'm not dividing by x. Okay. So what I could do is, I'll take my error, and if I multiply it by a, well then I can use the definition. So it's x minus x tilde. It's going to have ax minus ax tilde. Now, what can I do with that? Well, for instance, a times the exact is what? Yeah. So I have b minus ax tilde, but what is this? Yeah. It's the residual. So we have this relationship. AB is equal to R. So it's possible that it really depends on a matrix and also the particular vectors involved, like your right-hand side B, that it could work either way, that one of these vectors could be small and the other one surprisingly large. So we have to be careful about that. But we can also use this relationship to actually improve x tilde, to get a better approximation of x. But first I want to use this relationship to get ideas to how, like the worst case, as far as the error estimate in terms of the size of a residual. At least the size of a residual you would know. So if I just flip this around, error is A inverse times residual. And now I'm going to take norms, both sides, and I'm also going to divide by norm of x. And then I'm going to, so this is less than or equal to norm of A inverse, norm of R, and then I'm going to multiply and divide by the norm of A. Okay. Now, I've done this before, but the I can combine these since it's a less than or equal to. Since it's less than or equal to, and have B down below. Now the thing is, norm of B is less than or equal to norm of A times norm of X, but it's in a denominator, so I can go this way. And then I have up top, I still have the norm of the residual, but everything else I have, what can that be condensed into?
E. No.
No.
Identity.
No, we can't combine those because it's norm of A times norm of A inverse. If it was norm of the two together, then yes, but once they're separated, you can't do it. No, I guess that's what I was just telling her.
Oh no, that's the condition number.
Yes, it's a condition number, kappa of A. So this shows how bad it can get. That the relative norm of residual could possibly be amplified by as much as the condition number to give you a upper bound on the relative error. Yeah, so now it's relative because that's divided by x. All right. Now again, this is worst case, but it's important to be aware of that. Okay. So now, so I'm going to do an example highlighting what can happen when you have an ill-conditioned matrix. All right, now if I have this matrix, well, that would be a singular matrix. We have no inverse at all. But we're not going to work with this one. I'm going to make this 2-2 entry a little different from 1. So this is a matrix that's nearly singular. And in fact, we could compute the inverse of this exactly. And this is what it looks like. So we have all the entries of the inverse are plus or minus 10,000, except for the 1-1 entry, which is a whopping 10,001. So what we can do is we can compute the condition number pretty easily in, if we use the infinity norm. What is the infinity norm? Just in general, how do we compute it? Maximum row sum. Yeah. Okay. So we have the infinity norm of A, infinity norm of A inverse. Okay. So maximum row sum, we're going to get 2.001 for that, and then we're going to have, so we're taking absolute values, so it's 20,001. So it's pretty dang big. So it's 40,004 point something. 0001. Okay. Okay. So, so even a very small matrix like this can be quite ill-conditioned. I could have made it as bad as I want. Okay. So now I'm going to look at two right-hand sides, especially chosen to illustrate how bad it can get. Okay, so B1. Okay. So actually, these numbers are like perturbations of square root of 2. Or square root of 2 over 2, rather. Okay, so B2 is 6. Okay. So as you can see, the entries are all very close to each other. They agree to nearly 4 decimal places. So in fact, the relative difference is on the order of 10 to the minus 5. Okay. All right, so you think, okay, I can solve the system AX equals B1 and AX equals B2, and you would think that since B1 and B2 are so close together, so would X1 and X2. So I solve AX1 equals B1, AX2 equals B2, and what I would get is, okay, so we have 0.353, 536, 0.353553. Okay, and what about x2? I get 0.4964, 0.212132. So not even close. So in fact, if I look at the relative difference between x1 and x2, .4. So it jumped by several orders of magnitude. So this is what it means to have an ill-conditioned matrix. That slight change in the problem, like slight change in B, really can throw off a solution potentially by a large amount. Now I could also find right-hand sides, B1 and B2, that are close to one another, where X1 and X2 are also close to one another. It's kind of like basically bad luck. If you know the singular value decomposition of A, that would actually tell you what are the bad right-hand sides to have, because they, well, not just bad right-hand sides, but also bad perturbations. And in fact, I exploited that to come up with this example. Now, the trouble is a condition number is something that, and we can go ahead and have MATLAB compute it for you, but when you're working with very large matrices where computing time is at a premium, a condition number in any, regardless of what norm you're using, it's not easy to compute because you have to work with the inverse, and you don't want to compute the inverse. Now, formulas for a condition number in the 2 norm and I'm not sure if I gave this before, but in case I haven't. So that is the largest singular value of A divided by the smallest. Now, other formulas that we have for certain special cases, if A is symmetric, then the singular values are just the absolute values of the eigenvalues. So we can have like the spectral radius of A, which is the, so it's still the 2 norm condition number, which is the absolute value of the largest eigenvalue, and then we have the minimum absolute value of all the eigenvalues in the denominator. All right. Okay, but put another way, for a general matrix, it's also the square root of the largest eigenvalue of A transpose A over the square root of the smallest, because those actually give you the singular value. So a few different ways to express the condition number in terms of either eigenvalues or singular values. Only for the 2 norm. We don't have nice simple formulas for a condition number in any other norm, unfortunately. Okay. Now, there is one way to, because of a condition number, you really only care about its order of magnitude. Like, if the condition number of a matrix is like 10 to the 8th versus 5 times 10 to the 8th, the point is it's on the order of 10 to the 8th. It's bad. So if you just get some ballpark order of magnitude estimate, that gives you an idea as to what you're dealing with. So one guideline to estimate the condition number, and I do have a, if time permits, a method for estimating condition number that I'll get to later, but just to get a ballpark, one heuristic is that the size of the residual is roughly 10 to the minus t norm of A times the norm of your approximate solution, where t is digits of precision. So 16 in your usual IEEE floating point, double precision floating point number system. Okay. So then what you can do is once you have a residual, then you can compute an error estimate. You solve A E tilde is equal to R. So E tilde is an approximation of the true error that you wish you could have. So now you can use the fact that this error estimate you have is approximately A inverse R, but then if we apply properties and norms to that, and then we use this estimate of the size of a residual. So we fill in this down here, and we get 10 to the minus t, norm of A times norm of A inverse, so that's the condition number. And then we have the norm of our approximate solution. So then we can divide by that to get an estimate, okay, of the condition number just by rearranging. So the condition number is roughly your error estimate, the norm of that, divided by norm of x. So basically it's an estimate of your relative error times 10 to the t. So whatever error estimate you can get can give you an idea as to how badly conditioned your matrix is. Because if your matrix is very well conditioned, then there should not be much accumulation of round-off error during Gaussian elimination and substitution. So this should be quite small. It should be around 10 to the minus t. So you get closer to that ideal situation where your condition number is about 1. The condition number is always greater than or equal to 1. You'd love to have it equal to 1, but good luck with that. Okay. So any questions about this condition number estimate? But if possible, we'd like to do even more with residual and any error estimate that we can get than just estimate the condition number. We can actually use it to improve a solution. And that's, okay, now here's where you perk up your ears to get information that's relevant to the homework. So we can use this error estimate E tilde to improve X tilde. In fact, we can do it repeatedly. This leads to this algorithm iterative refinement. Okay. So what we do is you need to choose some error tolerance. So called TOL. How accurate you want the solution to be. And then some initialization here. So my first initial solution for convenience will just be 0. And then my initial residual, well, if I just stick with the definition, it is b minus a x0, but that's just going to give me b. And if you have an initial guess at the solution, then you could also use that for x naught. Okay, and now we go into a loop. Okay. So we go ahead and solve system A, EK is equal to RK. So we get our error estimate. So the first time around, R is just B. So E0 is just going to be our estimate of X. So this is something that we'd be doing anyway for solving AX equals B. But in later iterations, it's an error estimate. So this error estimate is incredibly small, and they use the infinity norm for convenience. Doesn't really matter which norm when it's a vector norm, but at least with an infinity norm, you're only doing comparisons. You're not actually performing any arithmetic. All right, so if your error is small enough, then you're done. And like in MATLAB, you might have a break statement. The point is you exit. Otherwise, we go ahead and update the solution. Because how is our error defined? Our error, E, is exact minus our approximate. So if we had the exact error, we can just rearrange this and add our error estimate onto our previous approximation. So go ahead and do that. So our new x, k plus 1, is our previous x, xk, plus our error estimate, ek. Now the next thing we need to do is actually it's the last thing we need to do, is update the residual. Now, there's a bad way and a good way to do this. I'm going to write the good way, and then, which is not what you might expect, and then explain why we do this. So the new residual, you might think, oh, we can just do b minus axk plus 1, but we're not. We're going to do rk minus a e tilde k. Okay. So that's our algorithm. So this algorithm is going to play a role, a central role in problem 3 on the homework. Now, as to why we do this, we use a definition that would just be b minus a x tilde k plus 1. Now, if I go ahead and fill in what x k plus 1 tilde is from over there, I have a x tilde k plus e tilde k. But now I'm going to group these together. So now I have b minus a xk minus a e tilde k. But using a definition of residual again, that's for previous residual. So it's r. All right. Okay. Now, it's all fun and games to do these manipulations, but can anyone think of a reason why? What's the advantage of using this formula over this one, even though mathematically they're perfectly equivalent? So if you're doing this on paper, it wouldn't matter. But why does it matter now?
Data is more expensive.
They both involve a matrix vector multiplication, so. Okay, I'll throw it in.
We already
What?
have our K, don't
We do, yeah.
we? We're using it, is that,
No.
or not necessarily?
I was gonna say wait. R sub naught is just B, but that's kind of
Okay. Okay. Yeah, that's what I'm going to do. As this algorithm proceeds, assuming everything is going how it's supposed to, and if this is converging to our exact solution, what should the residual be converging to?
Zero.
Okay, so we have a vector here, rk plus 1, that's going to 0. All right. So that is significant for what the answer is. That the result of what you're doing, you're using whatever formula, is producing a result that on a component by component basis, this vector is supposed to be small.
I mean, in the E is just the E sub k would just be all zeros and then the k component 1, right?
Oh,
Is
that's
different?
different E.
Different E, okay.
Yeah. Oh.
Okay.
I forgot all about that.
Yeah, I thought it was that.
Okay. Well, while we're talking about E,
Okay.
what is supposed to happen to E as this algorithm proceeds?
It's also supposed to.
All supposed to go to 0. Okay.
So then, as it goes
So-
to 0, that whole AE term should go to 0, right?
Right. Yeah, so you can say that both of these are meant to go to 0. But so now if we compare that formula, the one that I'm recommending here, with the other one,
But the one that involved B?
yeah,
X isn't.
x is not going to 0, and b is some fixed vector, could be
Right.
anything it wants.
But why?
Okay, so we got to a point where we're either subtracting two things that are supposed to be going to 0 to get something else that's supposed to be going to 0,
Right.
or we're subtracting two things that individually are not going to 0, but
Is this like squeeze theorem behind it?
no.
I'm just kidding.
Okay.
Forget it, but kind of sounded like it.
Much as I like working calculus and linear algebra, not this time.
It makes sense. I guess we just don't know how to put it in them.
Okay. All right. What is bad? Why is it bad to subtract two items that could potentially be large, when the result, we know it's going to be something small. Cancellation. This is a catastrophic cancellation situation. So we're vulnerable to that here, not so much here because these two things are going to zero anyway. So there's little details that make these algorithms really work when tried out for real. Okay.
So, excuse me, if you use b minus ax, then we have cancellation catastrophe.
Catastrophic cancellation, yes.
Yeah.
Okay.
It was French.
What?
It was French catastrophe.
French? Oh, okay. I was wondering what that was.
Sorry.
Okay. All right. Now, okay. Oops. Now, the thing is, it's very important for this algorithm to really work as intended, that your residual must be computed as accurately as possible. And what I mean by that is if your particular computer architecture supports some sort of extended precision arithmetic, then you'd want to take advantage of that, at least for this one step. So, for example, if you don't have that, if you are using double precision arithmetic for everything, then what that means is you can at least ensure that you get the solution that is exact in single precision. So, so the thing is, if you're computing everything with the same precision, like double, you're not going to get the exact solution in double precision. There needs to be something extra when it comes to residual. But having some assurance of the exact solution, even to like the 8 decimal places that single precision supports, that's still quite good. Okay. But you also need, and for it to work as advertised, that the condition number can only be so large. So your unit round off or machine precision should be small enough so that the condition number doesn't overwhelm it. Now, that still gives you a lot of wiggle room. But keep in mind, let's suppose you're aiming for the exact solution in single precision by doing double precision arithmetic for everything. And the unit round off that applies is for single precision. So again, in the order of 10 to the minus 8. So you get a matrix that's too badly conditioned for whatever precision you are aiming for, then this isn't going to help you. So more precision. I mean, all the problems in numerical analysis can be avoided completely if you just have enough precision for everything, but that comes with an increased cost, and I mean that literally. Also, slows things down. That becomes significant because if you're going to have floating point numbers occupy even more space than they already do, then you need more expansive memory and so forth. So I guess those powers that be that build computers have settled on this double precision, 8 bytes per number, as a decent compromise. Okay, and that keeps numerical analysts still in business. Okay. But the reason why this algorithm actually accomplishes anything at all is because what you get from EK is only an approximation. Because all the round-off error that happens, because in Gaussian elimination, an exact arithmetic does produce the exact answer, but of course you're not going to get that. Now, the homework problem that relates to this is a situation where, again, you are trying to solve some system and you have some way of solving it approximately, it's just a different sort of approximation. So you can do something like this to get your solution more accurately and efficiently by going about the most straightforward way. Okay, but when you all get to that problem, then we'll deal with the anguish then. Okay. Okay, so I mentioned earlier to talk about how to estimate the condition number. So here's an interesting way of doing it. And imagine this is actually an active area of research too. Now what I'm going to show you is a very crude approach to doing it, but it gives an idea as to how people go about these things. Okay. Because the problem is, condition number involves the norm of the inverse, and we don't want to compute the inverse. The inverse is very expensive to compute, or n cubed time. Okay. Now, just remind myself, there's something else I forgot to bring up about the inverse. I want to do that before class ends. Okay. So we need to get around that. Let's suppose we're solving some system, ay is equal to d. Then, of course, y is equal to a inverse d. And now we take norms. And I'll use the infinity norm for convenience. So now what we have is a lower bound on the norm of A inverse. So it's going to be norm of our solution divided by the norm of our right-hand side. And since it's easy to compute the norm of A, we can just multiply both sides by the norm of A and get a lower bound on the condition number. So I can say condition number of A in the infinity norm is at least norm of A, norm of Y, over norm of D. All things that we can easily compute. Now, so to illustrate how this could be done, I'm going to assume that A is upper triangular, so I'm going to call it T. So we're solving a system by back substitution. So we're solving Ty is equal to D, and so we have T11 Y1 plus T12 Y2, and so forth up to T1 and Yn is equal to D1, and so forth all the way down to a simple equation, Tn and Yn is equal to Dn. So the idea is we're going to choose the elements of D to all be plus or minus 1 in such a way as to make the elements of Y as large as possible. We want to drive up the norm of Y as much as we can. So what I can do is so Yn is going to be Dn over Tnn. So we just choose to be plus or minus 1. So that Yn, we'll just, for convenience, we'll just make it positive. So basically choose Dn to have the same sign as Tnn. Now we go to the next equation. So yn minus 1 by back substitution is dn minus 1, which we need to choose, minus t rho n minus 1 rho n yn over tn minus 1 n minus 1. So what we do is we choose dn minus 1 to be plus or minus 1. So dn minus 1 to have the same sign, no, opposite sign of the term that's being subtracted from it. That way, that increases that choice increases the magnitude of a numerator, it increases the magnitude of yn minus 1. And then we just keep going. So we just keep, so we're still choosing d minus 1 plus or minus 1 in order to make it happen. We could choose it to be something else. There are many approaches. Again, this is very crude, but at least it would give a lower bound for the condition number. Yeah.
Excuse me, so once we choose dn to be positive plus 1, dn minus 1 should be plus 1 also.
Well,
What would be?
like, it depends on the sign of the other elements. Like, here I've chosen yn to be positive. So if this is also positive, this entry of t, then this should be chosen to be minus 1.
Why? To give the negative sign?
Because then the numerator will have larger magnitude than the other choice. Yes, so if we make sure that this is a same sign operation, it's really an addition, then rather than subtraction, then we get larger magnitude. Okay. All right. Still want to make sure I get this in before we run out of time. Since I talked about why it's bad to compute the inverse. I don't know if I was somewhere else in my notes and I just missed it, but it's relevant, also relevant to the homework, so I want to make sure I cover it. Okay. Why we don't compute A inverse explicitly? Because it sounds tempting. You might think, okay, x equals b, then x is just A inverse b. So I might think, oh, okay, I'll just go ahead and compute the inverse and then multiply that by b. Now, I can use operation counts. Well, for one thing, if A is ill-conditioned, then this A inverse is not going to be very accurate, so that's one thing. But also, in terms of efficiency, it's a bad idea. So solving AX equals B the regular way, that incurs roughly 2/3 n cubed plus n squared floating point operations or flops. So LU factorization, forward substitution, back substitution. So the key thing is a 2/3 n cubed. Now, suppose we compute A inverse. Well, here's what you need to do. So you have 2/3 n cubed again for your LU factorization, assuming that we're doing pivoting. Then what you do is, so that's the first step. The second step is you solve Ly is equal to PEI, where this is now ith column of identity. Because you have A inverse is equal to identity. So column by column, you have A Bj is equal to Ej, where Bj is the jth column of A inverse. So that's what we're doing. We're solving Ax equals B n times, once for each column. So this is going to be, each forward substitution is order n squared. Then we get n cubed, because we're doing n of them. And then finally, we solve using back substitution. I'll use the same notation, bi is equal to yi for all I equals 1 up to n. So then again, the curves n cubed floating point operations. So grand total, we get 8/3 n cubed. So we're expending 4 times as many operations. Now you might think, oh, well, what if I'm doing many right-hand sides? Because once you have A inverse, this is a simple matrix vector multiplication. That's order. That's like 2n squared operations. It's cheap, but so this is not the only problem. This is also less accurate. Especially if A is ill-conditioned. Okay. So this is basically one of the commandments of numerical linear algebra. Never, ever, ever compute the inverse. So if you have an expression like a formula that involves the inverse, you think, oh, you're just solving a system. Ironically, in 461, 561, I teach about a method for solving systems of nonlinear equations called Broyden's method, which actually I think, when I taught 419, I think it came up in that class too, where the inverse is explicitly computed. So I don't want to say there are never exceptions, but it's something you don't want to do. Oh, I thought you had a question?
Oh no.
Or maybe the imaginary friend to your right had a question. Okay. All right. Okay. All right. So this is important for the homework, as examining the efficiency of various operations, and this is one of them. Okay. Okay. Now, if you could do something to your matrix to reduce the condition number, that would be great. And in some cases, you can. So what you can do is, instead of solving the original system Ax equals B, you can multiply both sides by some diagonal matrix D and solve that system instead. Or you can multiply A by a diagonal matrix on both sides. So D and E are both diagonal. And then you let X be equal to, so you solve this system. No. Okay. Oh, that's right. So then so you can figure this, so you solve this, you get your y, and then you just multiply by e to get your x. So working with diagonal matrices is great because multiplying them by vectors takes only n operations. Multiplying a matrix by a diagonal matrix takes only order n squared operations instead of the usual n cubed. So, so we'd like to be able to choose D, N, or E in order to reduce the condition number. Now, let me let A be, to illustrate what can be done, symmetric, but also positive definite, which is actually something I'm going to talk about a lot more next class. And for the time being, all right, so symmetric, and also has positive eigenvalues. Now, so in this situation, there exists a diagonal matrix D such that the condition number of the resulting matrix DAD is minimized. Now, that doesn't necessarily tell you what that diagonal matrix is. The point is, it can be proven that such a diagonal matrix exists, and you can do better to make a condition number as small as possible. And at least the expense is minimal. Okay. Now, wait a minute. Dang it. Okay, I'll just have to add to this statement. So this is true that condition number of a new matrix can be minimized if not only is it symmetric positive definite, but your matrix has what is called property A. And what I mean by property A is that you can shuffle the rows and columns of A using some permutation matrix pi. So in other words, there's some ordering of the rows and columns. It's the same ordering for both. That gives the matrix this structure. Diagonal matrix in these two blocks, and then the other blocks would just be transposes of each other. So D, this is very unfortunate notation because, all right, I'll call this D tilde. This is not the same as this D. But the point is you have a diagonal matrix. So if the matrix can be rearranged to give you a pattern like this, then the matrix is property A, and then there is a diagonal transformation that minimizes the condition number. And this kind of matrix actually does come up in certain applications, like it's solving differential equations, like using finite differences and such. So it's not some esoteric class of matrices. Okay. Now,
F is not diagonal. It's
F is, yeah, F can be anything.
thank you.
Okay. Now, I'm going to give a simple example of what can be gained from something as simple as a diagonal scaling. Okay. So a matrix is 2 by 2 case. Now, this is symmetric positive definite matrix. The sum of the eigenvalues is the trace. That's the sum of the diagonal entries. So it's 51. And then the product of the eigenvalues is the determinant, which is 50 minus 49, so it's 1. So it turns out what happens is one of the eigenvalues is approximately 51, the other is approximately 1 over that, to make sure that the product is 1. And that's bad because now this matrix is because it's symmetric and positive definite, the eigenvalues actually are the singular values, they're the same. Therefore, the condition number in the 2 norm is roughly, it's the largest divided by the smallest. That's going to be about 51 squared. So we're talking condition number of about 2,500. So that's pretty bad. Now, what we can do is, I'm going to let D be a diagonal matrix where I have 1 over square root of 50, the first diagonal element, and then 1 for the other diagonal element. And so when I compute DAD, this has the effect of making both diagonal entries equal to 1. And then the off-diagonal entries are both 7 over square root of 50. So in this case, we have the sum of the eigenvalues is the sum of the trace, which is 2. And then the product is going to be 1 minus 1 minus 49 over 50. So okay, so it turns out that the condition number in this case, the largest eigenvalue turns out to be 1 plus 7 over square root of 50, and the other is 1 minus 7 over square root of 50. And that turns out to be roughly 200. So we cut the condition number by more than an order of magnitude. So sometimes it's trying to, a lot of times matrices get ill-conditioned because the equations are badly scaled. Like one, you might have the coefficients in one equation have significantly different order of magnitude than the coefficients in another equation. So if you try to balance those out a little bit, that can improve the conditioning of your matrix. This is something that MATLAB sometimes complains about, saying like, well, certain matrix seems to be badly scaled. So sometimes it's easier than you think to like basically repair your system of equations so that it has better properties numerically.
So would the second one be, so the first one would be considered ill-conditioned?
What is considered ill-conditioned is kind of murky because
Is it like relative to the problem?
yeah, also it's relative to how much precision you have. So really all I can say is, well, at least this is better conditioned than what we had. I personally would not get gray hairs over a 4-digit condition number. But that's because when you deal with PDEs, the condition numbers always tend to be bad. So that's something you just kind of get used to. But yeah, I would have a problem like if we were talking like, you're 10 to the 8th, because then it wipes out your signal precision. Okay, now, whoops. All right, so the last thing is equilibration. Okay, so what you do is, so you set A0 to first be the original A, and then I have A, so sup 1/2 is set to be A0 times some diagonal matrix D, where what you do is you choose D1 so that so all of the row sums are equal. So now the way I can do that is, because the idea is, if I take a sum of, for a particular row of the new matrix. So that's going to be di, and I'll choose this to be positive, and then I have absolute value of aij. So what I can do is, like, for instance, so this is the row sum. Of the absolute values of all entries in row I, but I can pull the di out of the sum. So I can just say if I want all the row sums to be equal to 1, for instance, I can do that. So I can choose each di to be 1 over the previous row sum. Okay. Okay, so choose ones are all equal to 1. All right, so di is just that. Okay. And of course, that row sum can't ever be 0, because the matrix is a 0 row. It's not invertible anyway. Okay, so now I've made all the row sums equal to 1. And then what I do is set A1 to be equal to A1 half times a different diagonal matrix, E1. So this has column sums equal to 1, because if I'm multiplying by diagonal matrix on the left, it scales rows. If I'm multiplying on the right, it scales columns. So then I can repeat the process. So a k plus a half is equal to dk ak. To make a row sums equal to 1 again. And then ak plus 1 is equal to ak plus a half times ek. Repeat this until convergence. And under modest assumptions on A, this actually will converge. Because what happens is, you make a row sums equal to 1, then when you make a column sums equal to 1, the row sums are no longer equal to 1. You've undone that. But you keep going, eventually it does work out that way. That you get all the row and column sums equal. And this is another way to have a system as well scaled as possible. Hopefully that also reduces the condition number. Okay. All right. So that actually concludes the coverage of general systems of linear equations. There is no class next week. I'm away to SIAM meeting. I don't come back until too late on Thursday to have class. Okay, 2 of you are at that conference also. So the following week, so March 6th? No, it's March 7th. Is where we pick up again with special systems of equations. So we'll talk about positive definite systems and banded systems. Okay. Recording. Okay. A mistake was pointed out. Here this should be dk plus 1. Just like how I have d1, e1 here. And that should also be k plus 1. Okay, so that's the equilibration algorithm. Of course, it's in notes. Okay. Is that